All right, there we go. All right, so good afternoon, everyone. How's everyone doing today? Good, good to hear. All right, so today we're going to continue. The plan is to continue with our lecture notes on step and impulse functions. So I have a couple of examples. We'll actually be solving differential equations with them today, so that'll be exciting. But I think obviously the most probably pressing thing that you see on the screen now is information about our midterm exam. So let me go over that first. So I did post the solution for homework 1 and homework 2 today. I did grade your homework 2 today as well. So those are posted on Canvas for you. So you will find them in the week 6 page. So if you go to week 6 on the Canvas site, you'll see that there are 2 PDFs at the bottom. One of them is homework 1 solution, the other is homework 2 solutions. Okay. I do plan on posting the solutions for homework 3 before your exam as well, but obviously I can't post it yet because you guys are still working on it. So I will post homework 3 solutions early next week. Okay. Okay, so midterm 1. So midterm 1 is planned for next Thursday, so that is March 5th. So let's go for the format of the exam first. So the exam is going to start with 4 short answer conceptual questions. So very similar to what you see in the homework. They're obviously not going to be the same questions from the homeworks, but I always tell people that if you can answer if you can answer the homework problems, you'll do just fine on the exam. So hopefully you guys are getting used to that kind of format. And then after those conceptual questions, there will be 3 problem solving questions, which the whole theme of this first part of the class is just differential equations. And so you can expect there to be 3 differential equations for you to solve. Okay. And if you're a little bit savvy, you can probably kind of already tell that we've had you're going to have 3 homeworks up until that point in the semester. So you can expect each of the problem solving questions will represent each of the homework assignments. Okay, so you have one problem on the exam that has to do with first order ODEs, another problem on the exam that has to do with second order ODEs, and the third question will have to do with Laplace transforms. Okay. So again, they're not going to be exactly the same problems that you see in the homeworks. But if you can do those problems, then you'll have a really good chance of doing well. Okay. Now, in terms of what to bring, obviously you need to bring your writing utensil, bring a pencil, pen, whatever you're comfortable with. Bring a calculator as well, so a calculator can help speed up some calculations. But I think probably the most notable thing to bring is that you can bring an 8.5 by 11 sheet of notes. And so you can use both sides and you can write it, you can type it. My only requirement for the cheat sheet is that you'd be able to read it during the exam. So no magnifying glasses, no weird, meta glasses or anything like that to kind of zoom in, right? And so just have to be able to read it with your naked eye. Okay. You don't have to write down the Laplace table. I will provide that for you. So I will provide an additional sheet which has all the Laplace transforms that you've been using on the homework. So don't worry about that. But you can write whatever else you can on the cheat sheet. Okay. One other thing that I forgot to mention here is that I also will be posting a study guide. And I will probably get that up to you by tomorrow. Okay. Probably should have had it up today, but I just kind of slipped my mind today. But I will post a study guide. So the study guide you'll see is just a collection of all the learning objectives that we've been going over in the class. So I think that's great studying for the conceptual questions. And so if you can answer all the learning objectives, that's great. But it also kind of summarize all the different problem solving skills that you'll need to do as well. Okay. So for studying, right? So people always ask me, what's the best way to study for the exams? So I would definitely start with the homeworks. And so, definitely, the style of problems that you see on the homework, is the same style it's going to be on the exam, because they have the same author, which is me, right? And so, if you can do the homework problems, you can do well on the exam. And I would definitely check out the study guides to kind of make sure that you're covering all your gaps. Okay. Okay. Any questions on the format of the exam or in terms of what you can bring? Okay, so with that said, I do have a proposal for you guys. And so I was made aware recently that next Thursday is going to be a very busy exam day, as typically is the case, right? And so, I know a lot of midterms tend to converge on the same week, on the same day. So I was wondering, would you guys be open to postponing the exam? And so instead of being Thursday, March 5th, we would have the exam on Tuesday. I believe that is March 10th. Is this official? It's not official, so I'm putting it up to an unofficial vote. So would anyone be opposed to the new date, or everyone feel strongly about the old date? New date? Old date. Okay. Does anyone want to do, or how does everyone feel? How's that Thursday looking for everybody? You prefer to keep the old date? Okay. All right.
We can do a vote, hands up vote.
How about this? Just so people don't feel embarrassed to vote or not. I'll put a poll on Canvas, so that everyone kind of vote on whether they want the new date or the old date. That way, it's because when you do it in the lecture like this, then it's more. We'll do it the official way. We'll do kind of the real way for them. Okay. So I'll put a poll on Canvas this evening. I'll go and post a study guide this evening too. I already have it written. I just forgot to post it. And so make sure you vote in that poll, and then by Thursday, we'll have an official date for the exam. Okay. All right. Any questions on anything else before we get started for today? Okay. All right. So let's go ahead and get started. Okay, so where we left off, or what we were talking about last Thursday, was step and impulse functions. Or I guess specifically, we only have gone over step functions so far. Okay, so just to kind of refresh your memory, a step function is essentially a function with a discontinuous step, and so it goes from 0 to 1. Okay, so it looks like this. All right, where the horizontal axis is time. We have some kind of offset here, so we say that the step starts at some some value of t time, which is a, right? Right, and then our step function, is 0 up until where the step occurs, and then it jumps up to a value of 1. Okay. So remember, this idea of a step function is, what we typically call like an engineering function. And so it has a lot of strange mathematical properties where, you can't really tackle with traditional math theory. But, for a lot of systems that we work with in engineering, something like this is very helpful. Okay. And so primarily, we're going to be using this function to model forcing functions that either, start and stop abruptly. Okay. So remember, one of the examples that we went over previously, or that we talked about, was, like a light switch that's turning on and off, right? And so there's a lot of situations like that in engineering. Okay. Or another common case that, we'll see in the first example today is a forcing function that changes form or changes, structure abruptly from one to the other. Okay. Or in other words, we can call that a discontinuous forcing function. Okay. All right. And so the mathematical form for this, or the way that we denote this step function, is by the symbol u. Okay. So this function here is u of t minus a. Okay. So that tells us that our step here, or the place where the step occurs, is at it. Okay. Okay. So last time, we went over, just the properties of the step function. We went over its Laplace transform. We went over the corresponding second shifting theorem, right? So we have we've done all the preliminaries, and so now we're now finally ready to actually use this in some problems. Okay, so let's go ahead and do that. So let's start with an example today. What's up with my iPad? It's on the fritz. Okay. All right, so let's solve the following differential equation. Okay, so we're just going to solve for the solution to the following ODE, or I guess you can call it an initial value problem because we also need initial conditions as well. Okay. All right, so we have d squared y dt squared plus 4y is equal to g of t. Okay. Right, so the differential equation is fairly straightforward. So we just have, a second order derivative plus 4y. Okay. But what's going to be interesting here is this forcing function g of t. So this forcing function, we're going to give it a piecewise definition. Okay. And so it's going to have a value of 0 when t is less than 5. Okay. Right, at t is equal to 5, it's suddenly going to change form. So we're going to have a discontinuous kind of abrupt change. So it's going to have a value of t minus 5 divided by 5. So basically a linear ramp when 5 is less than or equal to t, which is less than 10. Okay. And then this function is going to level out to a value of 1 when t is greater than 10. Okay. And then before I forget, let me give you the initial conditions. So initial conditions, we have y of 0 is 0. And then the initial velocity dy dt at t is equal to 0 is also 0. Okay, so we're starting completely from rest, and so we don't have any initial displacement or any initial velocity. But we do have this kind of ramped forcing function. Okay. So first thing I'm going to do, I'm going to plot this. And so let's plot our g of t. Right. The plot isn't essential for this problem, but it just kind of helps to visualize what we're doing. Okay. All right. So according to this definition here, our forcing function would be 0 up until t is equal to 5. Okay. All right. So we're basically going to have no action until 5 seconds, and then at 5 seconds, our forcing function is going to start to ramp up. Okay. And it's going to ramp up to a value of 1. Right, at t is equal to 10. Right, and so it's basically going to slowly ramp up to 1, and then once our forcing function reaches the value of 1, it's then going to plateau at that value and then maintain it for the rest of the problem. Okay, so it looks like a ramp essentially. Right? Okay, so we want to find the solution to this differential equation, and we're going to be using Laplace to do so. Okay, now for a problem like this, technically you can use the traditional way, right? And so you can solve for this for the solution here using characteristic equation. We can use our undetermined coefficients, but because of the discontinuous forcing, it's doing so would be very cumbersome. So basically you have to solve. So basically every time the forcing function would change form, that would be a separate differential equation that you'd have to solve. So you basically have to solve 3 different problems, to get one solution. Whereas with Laplace, we can kind of just do it all at once. Okay. Okay. So our strategy or our way that we're going to solve this is we're going to be using Laplace transforms along with step functions. Okay. So we'll be using step functions to represent our forcing function. And then once we have that, then we can just use our typical Laplace kind of method to, take Laplace and algebraically solve for the solution. Okay. Okay. Any questions on just the setup for the problem before we get to solving it? Okay. All right. So let's go ahead and solve. Right? So when you have a discontinuous forcing function like this, the first step is always going to be to represent your forcing function as a single expression. So step 1, represent forcing function. Okay. Because right now, our forcing function is in three separate pieces, right? And so, we want to represent that as a single expression, just so that we can take its Laplace transform. Okay. All right. So I'm going to write down the g of t again, just so I don't have to scroll up and down, right? So g of t has a value of 0 when t is less than 5, has a value of t minus 5 divided by 5. When t is between 5 and 10, and then evens out when t is greater than 10. Okay. Okay. All right. So this is very similar to the last example that we did last Thursday, right? So we have basically, this function here is kind of broken into different parts. But one way that you can see it is that, each of these parts are kind of turned on and turned off, according to their given domain. Okay. Okay, so let's start with the first section here. So the first section says that our function here has a value of 0 between 0, basically t is equal to 0 and 5. Okay, so we'll start with this. Okay, so g of t is equal to 0. Okay. Right, so we're going to turn on this section of the function with the step function. So we're going to say this function turns on at t is equal to 0. Okay. So we're going to multiply this by u of t. And then we're going to turn it off at t is equal to 5. So we're going to subtract u of t minus 5. Okay. Now, of course, all that is a moot point because, we're multiplying this by 0. But, I just wanted to kind of illustrate that to you. Right. So, of course, 0 kind of supersedes this as all equal to 0. But, just for the sake of completeness, we'll kind of just keep it there for now. Okay. Next section. So next section, we have t minus 5 divided by 5. We're going to turn on the section at t is equal to 5, and we're going to turn it off at t is equal to 10. Okay. All right. So we're going to have t minus 5 divided by 5. Okay. And then we're going to turn it on at t is equal to 5. So we're going to multiply this by u of t minus 5. And we're going to turn it off at u of t minus 10. All right, and then we have our final section here. So the final section, we're just turning it on. So we're not turning it off. It's just going to be 1 for all eternity. Okay. So this one is we're going to add a plus 1 times u of t minus 10. Okay, so that's when we're turning it on. And we're not turning it off, so we don't have to subtract these things. Okay, good. All right, so that's basically how you take a discontinuous function and you represent it with steps. And so you basically take each section of the function and then you take note of when that function turns on, you multiply that by the specific step function, and you subtract the step function whenever it turns. Okay. Okay. All right, so let's go ahead and simplify this because we are going to take its Laplace transform in a second. Okay. All right, so of course, the first term in orange, that just goes away, right? It's because 0 multiplied by a step function is just 0. Okay. And then what I'm going to do from there is I'm going to distribute. Okay. We have g of t is equal to t minus 5 divided by 5 multiplied by u of t minus 5. Okay. Minus t minus 5 divided by 5 times u of t minus 10. Okay. Plus u of t minus 10. All right, good. Okay, so from here, technically we can take this and plug it back into the original differential equation because we've basically accomplished our task, right? And so we've taken our forcing function and now we've represented as a single expression using these step functions. Okay, so what we just found here is exactly equivalent to its piecewise definition up here, right? But this form down here, this is much more tenable or much more convenient to use in our Laplace expression. Okay. Okay, so with that said, we're going to do this eventually. And so let's go ahead and just take this Laplace transform. Okay. So we take its Laplace transform, we're going to get a capital G of S. Okay. Okay, and so in order to take the Laplace transform of this, we're going to need to make use of our second shifting theorem. Okay. Okay, so let's look at the first expression first. So we have t minus 5 divided by 5 multiplied by u of t minus 5. Okay, so we can see here that we have a shift of 5, right? So from our step function here, we have a shift of 5. And so we know that its Laplace transform, we're going to multiply by e to the minus 5s, right? Remember, that's how we apply our shift, right? And so whatever shift that we have in the time domain, that's going to be an exponential in the Laplace domain. Okay. I'm going to go ahead and pull out the 1/5, just because, the 1/5 doesn't affect our Laplace transform. It's kind of just along for the ride. Okay, so when we take its Laplace transform so far with e to the minus 5s over 5, okay? And then remember the way that we apply our shifting is that, once we have applied our shift, right? So once we multiply by the exponential, we can then take the Laplace transform of what I call the base function, okay? And so if we look at t minus 5, right? So the base function without the shift, right? So we basically just undo that t minus 5, right? So our base function is just t, right? Right? And so Laplace transform t, we can do that. So we know the Laplace transform t is 1 over s squared. Okay? So that Laplace transform of that first term is e to the minus 5s divided by 5s squared. All right, any questions on how we got that first Laplace transform there? Okay. Okay, so now let's do the second term. Okay. This one's very similar, right? And so we have basically the same function, t minus 5 divided by 5, and we're going to multiply by step function, but our step function here has a different shift. Okay. So for this term right here, shift does not match function. Okay. Right, so that u of t minus 10 means that we have a shift of 10, but we look at our function is only shifted by 5, right? So we only have a t minus 5 there, okay? So, we tackled cases like this last time as well, right? And so in order to tackle this, okay, you need to kind of tackle it in 2 steps. And so first we can go ahead and apply the shift, right? In the Laplace domain. Okay. And so the way that we do that is that we're multiplied by an exponential function with the shift. And so since our shift is 10, we're going to multiply by e to the minus 10s. Okay. And then from there, what we're going to do is that we're going to go back to our original function and then replace it by a function that is, basically is the reverse of the shift that we just did. Okay. Okay. All right. So what does that mean, right? So, the shift that we just did was a shift of 10, right? And so in order to kind of undo that shift, we need to plug in t plus 10 into our original function of t. Okay. And then once we do that, whatever kind of results from that, we can just take the Laplace transform of that. So it's a few steps, and so that's why I kind of listed them all out here. I know I kind of made a mess, right? So I know I kind of left the G of S hanging there, but we'll kind of clean up in the end. Okay. Well, let's kind of summarize this in the math, because that's what you're actually going to be doing, right? Okay, so let's take the same process and then apply it to our function here, right? So our function here is t minus 5 divided by 5 multiplied by u of t minus 10. Okay. Okay. Actually, let me move this over to the right a little bit. Okay. So let's go ahead and take the Laplace transform of this entire expression, okay, because that's what we want to do. Okay. Okay. So let's just apply our steps kind of step by step. So first thing is we are going to apply our shift, right? And so first we're going to multiply this by e to the minus 10s. Okay. So we have e to the minus 10s just like that. Okay. So that kind of eliminates the step function from our expressions. We don't have to worry about that anymore because we already applied our shift. Okay. But now that we've applied our shift, we need to kind of plug that opposite shift in for our original function here. Okay. So now instead of taking the Laplace transform of t minus 5 over 5, we're now taking the Laplace transform of, okay. So instead of t, we're going to plug in t plus 10. Okay. We still have the minus 5, all divided by 5. All right, and of course we can simplify this, and so we simplify this as e to the minus 10s, Laplace transform of. Now we have a t plus 5 over 5. Okay, and then that we can do, right? Because we take the Laplace transform of t over 5. Plus Laplace transform of 5 over 5, which is just 1. Okay. All right, so we go ahead and do that. We get e to the minus 10s. Laplace transform of t over 5 is 1 over 5s squared, plus Laplace transform of 1 is just 1 over s. Okay. Okay, good. It all fits on 1. Okay. So this is kind of a good, I didn't plan it this way, but thankfully it worked out. So this is kind of a way to kind of apply our shifting theorem for cases when our shift does not match our function. Okay. Now, technically, you can apply this exact same process for cases when our shift does match, right? And you'll see that you'll get kind of the exact same thing. So, if you just want to memorize just one process, I would just memorize this one. It's a little bit more lengthy. It's more lengthy than just kind of noticing that the shift is the same. But this is kind of the process to follow every time you apply the shift. Okay. All right. Any questions on this? Okay, good. Okay, so that's the second component of our G of S, right? So let me go ahead and write it back in. So let's go ahead and plug this back in. Okay, so G of S is equal to, we still have our original term, so that is our first shifted e to the minus 5s divided by 5s squared. Okay. Right. To this, we're going to subtract our shift of 10, right? So we're going to subtract what we just found here. We're going to subtract e to the minus 10s divided by 5s squared minus e to the minus 10s over s. Okay. So those two terms that we just found, those came from the mismatch shifting term that we just solved for. Okay. Okay, but that's not the last component of G of S. Okay. So our last component of g of s is we have a positive u t minus 10. Okay, and thankfully that one is very easy to take the Laplace transform because that's just a simple step function by itself. And so that is an e to the minus 10s over s. So this right here, this was the Laplace transform of u of t minus 10. All right. And so luckily here, we do have a little bit of simplification, so we can cancel those last two terms out because they are exactly the same, right? And then finally, what we get for our g of s is e to the minus 5s all over 5s squared minus e to the minus 10s over 5s squared. Okay. We're not done with the problem yet, right? So we have to go back and actually solve the differential equation. But this is a great step, right? So now we can take the Laplace transform of a forcing function, we have it as a single expression. So now we can, solve our differential. All right, any questions on how we got to this point here? Okay, good. All right, so let's go back to our differential equation. So now that we have our forcing function here, let's go ahead and plug it back in. Okay. All right, so next step is to just kind of do our typical kind of Laplace, Laplace, I would say algorithm to solve our differential equation. Okay, so let's go back now and let's take the Laplace transform. Okay. We're going to do that for the entire differential equation. So our differential equation in this case was d squared y dt squared plus 4y is equal to g of t. Okay. I'm not going to write what g of t is. We just spent the last 20 minutes talking about that. Okay. So let's take the Laplace transform of this entire expression. Okay. We're going to take the Laplace transform of each term individually. Okay. So first we have the Laplace transform of the second derivative. And so that, remember, is s squared big Y of s minus s little y of 0 minus dy dt at y is equal to, or t is equal to 0, excuse me. Okay. So everything in the square brackets there, that is the Laplace transform of the second derivative. Okay. Plus 4 times y of s. Okay. So there's no derivatives on the 4y term, and so that just Laplace transform to 4y of s. Okay. And this is equal to Laplace transform of our forcing function, which is big G of s. Okay. Which we know what it is because we just solve for it just literally right there. Okay, good. All right, so from here, the next step is always going to be to plug in our initial conditions. Let's plug in for y of 0 and dy dt at t is equal to 0. Okay, so if we go back, way back to kind of the start of the problem, we know that y of 0 is equal to 0. Okay. And we also know that dy dt at t is equal to 0 is also 0 for this problem. Okay. So that kind of saves us some work, so we don't have to worry about any initial conditions. Okay. So we go ahead and simplify, right? And so we have basically s squared plus 4 multiplied by big Y of s. Okay. And this is equal to g of s. And let's go ahead and plug in for g of s at this time. So we have e to the minus 5s divided by s squared, 5s squared minus e to the minus 10s divided by 5s squared. Okay. And so now that we've Laplace the entire equation, the next step is just to solve for y of s, which is simple in this case. So algebraically, solve for y of s. Okay, so we have y of s is equal to, we're just going to divide both sides by s squared plus 4. This is equal to e to the minus 5s divided by 5 s squared multiplied by s squared plus 4 minus e to the minus 10s divided by 5 s squared plus 4. Okay. Okay, good. All right, so now that we've solved for y of s, our last step is going to be just to invert this. Okay. But unfortunately, we don't have a table entry that looks like this function, right? So remember, when you're taking the inverse of things with the shift, we just ignore the shift for now, and then we apply the shift at the very end. Okay. So first, let's invert kind of the base Laplace expression. Okay. So luckily for us, both of these terms here have the exact same expression, right? So the only thing that's different about them is the shift, right? And so essentially we have 1 over s squared times s squared plus 4. Okay. The 1/5 we'll bring back in later, but we'll just take the Laplace of this one first. Okay. Okay. But of course, we can't do this, and so we do have to do partial fraction decomposition. And so we do a partial fraction decomposition. We have a over s plus b over s squared. Okay. So remember, that's how we decompose the 1 over s squared, that we have to do kind of all of its components because it's basically a multiple root. Okay. Plus cs plus d all over s squared plus 4. Okay. So remember that s squared plus 4, that is a quadratic function that we can no longer factor anymore. And so in order to do the partial fractions, we have to do a linear function up top. Right? And so that's why we have cs plus d up top. Okay. Okay. All right. So let's just, we've done, quite a few of these already. So let's just kind of go quickly and perform these partial fractions. Okay. Okay. So first thing I'm going to do is I'm going to multiply by the entire denominator. All right, so we're going to multiply this entire expression by s squared times s squared plus 4. Okay. So that's going to eliminate the denominator on the left-hand side. So left-hand side, we just have 1. Then on the right-hand side, that denominator is going to cancel out with certain components in the denominators for each of the terms over there. Okay. So we have a times s squared plus 4 plus b times s squared plus 4 plus cs plus d multiplied by s squared. Okay, and of course our goal here is to solve for a, b, c, and d, so let's go ahead and do that. Okay. So remember, the way that we do this is that we distribute all of the terms on the right-hand side there, and we group them by, and we kind of group like terms together according to the powers of s. Okay. Okay, so on the right-hand side, let's distribute everything first. And so we have an a s cubed plus 4as plus bs squared plus 4b plus cs cubed plus ds squared. Okay. All right, so now that we've distributed everything, we can go ahead and group all the like terms. And so we're going to group them by powers of s. Okay. All right, so first we have the s cubed terms. And so for the s cubed terms, we have an a and a c. That's a plus c. Okay. Next, we have the s squared terms. So for s squared terms, we have a b plus d. Next, we have the S terms, and so multiplied by S, we have a 4A. Okay. And then for the constant terms, we just have a 4B. And all this is equal to 1. Okay. Okay. All right, so let's go ahead and set up our system of equations. So we're going to equate basically the terms on the right-hand side and the left. Okay. All right, so for our S cubed, right? Sorry, that's S cubed, right? So S cubed on the left-hand side, we don't have any contributions to S cubed. So left-hand side for S cubed is going to be 0. Okay. And on the right-hand side, we have just an A plus C. Okay. For S squared, we also don't have any contributions to S squared on the left-hand side, so that's going to be 0. And this is going to be equal to B plus D. Okay. For our S term, and so our S on the left-hand side, we don't have any contribution to S. So left-hand side is going to be 0. And the right-hand side, this is going to be equal to 4 times A. And then finally, for our constant term, this is the one term that doesn't have a 0 contribution. So on the left-hand side, we do have a 1. And this is equal to 4B. Okay. All right, so 4 equations, 4 unknowns. Luckily, this system is not too bad because some things going to come out right away, right? So first thing we notice here is that A is equal to 0, right? So we solve the third equation, we divide by 4, we get A is equal to 0. Next thing we notice is that B, we solve the last equation, is equal to 1/4. We plug those two things back up here. We can see that if A is 0, that means C must be 0 as well, right? Because we have A plus Z is equal to 0. If A is equal to 0, that means C must be 0, okay? And then finally, we get D, right? We plug in the value for B into this expression here. That means D must be a minus 1/4. Okay. And so with those coefficients in mind, we can go ahead and complete our partial fraction. So our partial fraction decomposition, 1 over S squared times S squared plus 4 is equal to 1/4 times 1 over S squared minus 1 over 4 times S squared plus 4. Okay, good. Any questions on how we did this partial fractions? Okay, good. All right, so let's go ahead and plug this back in. We're just about there. Okay. Okay, so we plug this back into our original differential equation, right? And so we said that y of s is equal to, okay, we have e to the minus 5s over 5 multiplied by this guy here. So we're going to do multiply by 1 over 4 s squared minus 1 over 4 s squared plus 4, okay, minus e to the minus 10s over 5, okay, multiplied by the same thing. So 1 over 4 s squared minus 1 over 4 s squared plus. All right. So now we can finally perform our inverses, right? Because everything in the parentheses there, that is a term that we have in our Laplace table. All right, so now we do have a shift, right? So we do have our shift of 5 and our shift of 10. But remember, the way that we take these inverses, that we kind of do it in 2 steps. So first thing is we inverse the functions without the t shift. So I'm going to keep the t shift on the outside. So we're going to have e of e to the minus 5s divided by 5. Okay. We're going to take the inverse of 1 over 4s squared. So that is t squared, or excuse me, just t over 4. Okay. Minus inverse of 1 over 4 times s squared plus 4. So that is a sine. Okay. And so, for the sine, our omega here is 2. So that means we need a 2 up in the numerator, which means we need to divide by 2. So this is 1 over 8 sine of 2t. And we're going to do the exact same thing on the second term, because the second term has the same, same Laplace expression on the inside, just with a different shift. So this is minus e to the minus 10s divided by 5 multiplied by t over 4 minus 1 over 8 sine of 2t. Okay, so now we have this kind of weird expression where we're kind of in between both realms, right? So we have our functions of t, but we still have our shifts that are in the Laplace domain. All right, and then the last step to solve this problem is we're going to apply our shift. Right, so now we're going to take in those e to the those exponential terms there. Okay, so remember the way to apply the shift, we need to do two things, right? And so first thing we need to do is we need to replace t everywhere with the shifted version of the t. Okay. Right, so I think that's probably the big one, the big one that most people remember. But don't forget the second step too, right? So the other step that we have to do when we apply our t shift is we have to multiply by a step function with the same shift. Okay. All right, so let's go ahead and do that. I'm going to go ahead and distribute the 1 over 5 through as well. Okay. All right, so finally, we can go ahead and write our expression here. So we have y of t is equal to, okay. So first we have t divided by 4, shifted by 5. And so this is going to be a t minus 5. Okay. Divided by 5 times 4, which is 20. Okay, so that's t minus 5 divided by 20. Minus 1 over 40 sine. Okay. Same thing, we're going to replace t by its shift of 5. So sine of 2 times t minus 5. Okay. Right. So all I've done there is, I've simplified this a bit. So I've multiplied by 1/5, but I've also replaced t by its shift. Okay, so t becomes t minus 5. And then we need to multiply by its corresponding step function. So we're going to multiply this by u of t minus 5. Okay. All right, and then finally we have our second term there. So we have basically the same thing, but shifted by 10. Okay. So we're going to have a minus, right? So if we shift by 10, we're going to have u of t minus 10 divided by 20 minus 1 over 40 sine of 2 times t minus 10 multiplied by u of t minus 10. And that right there is our final solution. Okay. So I know that took a while, right? So we basically spent 45 minutes on the same example, but I try to be as kind of explicit with every single step, because with Laplace, it is nice that you can do it all in one step, but there are so many kind of little things that you have to do along the way with the shifting, with the partial fractions and everything. So, I wanted to be kind of very detailed in this example to kind of hopefully kind of illustrate everything. So, if you're kind of looking for a quick example, I'm sorry, this is not it. This is kind of the 45-minute example, but hopefully you kind of understand every step along the way as well. Okay. All right, so I do have one more example. So for this next example, we'll go a little bit faster. So hopefully you'll see kind of a more, how you guys would probably solve it kind of in real speed. But before we get to that, are there any questions on this example here? Okay, all right, so let's do one more example. This will probably be the last thing we do today. Okay, so this example is a bit more applied. So we're not just going to be looking at a math problem now, but let's look at an RC circuit. All right, we're going to look at an RC circuit with a switch. Okay, all right, so let's kind of draw the schematic. Okay, so RC stands for resistance, so we do need a resistor. We have a capacitor, okay, that's what the C stands for. We're going to have a switch, and so we're going to assume that we have a switch that looks like this simply. Okay? And then we have it connected to a DC battery here. Okay? Okay. All right, so this switch is going to be switched. It's going to start in the off position, and then we're going to switch it on at some point, and then we're going to switch it off again. Okay, so a very stereotypical, very typical case you would tackle with step functions. Okay. Okay, so our differential equation for this. So we're going to be looking at the charge on the capacitor. So the differential equation is dq dt plus q divided by RC is equal to E of t divided by R. Okay. Where E of t is equal to, okay. Right, so we said that the battery is going to be disconnected at first, and so it's going to have a value of 0 when t is less than some number a. So we're going to flip it on at t is equal to a. So then our battery is going to have our forcing function is going to have a value of E between t is equal to a and t is equal to b. Okay. And then at t is equal to b, we're going to shut it off again. And so it's going to just abruptly kind of go back down to 0. Okay. All right. And then the last piece of information we need before we start solving is the initial condition. And so the initial condition. Okay. So unlike the previous problem, we are going to assume that we do have an initial condition here. So it's not just going to be 0. But we're going to say it's a generic kind of Q naught. Okay, so that Q naught there represents the initial charge on the capacitor. Okay. All right, so just like we did in the previous example, we're going to be using Laplace transforms to solve for the solution of Q of t. Okay. Any questions on just the setup for the problem? Okay. All right, so first thing you should notice, and so we haven't seen one of these in quite a while, but you should notice from our governing equation here, this is a first order differential equation, okay? So that's good, because first order equations typically are much easier to solve than second order. Second order is quite an ordeal, as we just saw here, okay? But you can apply Laplace transforms to first order equations and second order equations. The process kind of still remains the same. Okay. So first thing we're going to do, just like the last example, is that we're going to take our forcing function E of t and represent it using step functions. All right, so unlike the previous example, I'm just going to omit the parts where the E of t is 0. So, we don't really care what happens between, 0 and t is equal to a, and the section where where t is greater than b, just because those are just 0. So I'm just only going to focus on the section where E of t is non-zero. Okay. Okay. So when E of t is non-zero, it has a value of E, which is a constant. Okay. We're going to turn it on at t is equal to a. So we're first going to multiply this by u of t minus a. And then we're going to turn it off at t is equal to b. So we're going to subtract u t minus b. All right. Let's take its Laplace transform, right? So we are going to need to do it eventually. In this case, it's very simple. So our function here is just constant. Kind of unfortunate that we use capital E already, so there's no distinction, but that's fine, right? So our Laplace transform E of S is going to be equal to E. First, we have a shift of A, so it's going to be multiplied by E to the minus AS. Okay. Laplace transform of the step function is just 1 over S, and so we have E times E to the minus AS over S, minus the same thing for the second term. So E times E to the minus BS divided by S. Okay. Okay, good. All right, so let's go ahead. Now that we have our expression for our forcing function, we can go ahead and plug it back in and then take the Laplace transform of our entire equation. Okay. Okay, so let me write down our differential equation again. So we have dq dt plus q over rc is equal to E of t over r. Okay, so let's go ahead and take the Laplace transform. Okay, so let's take the Laplace transform of each term individually. Okay, so first we have the Laplace transform of dq dt. Okay. All right, so for a first order derivative, this Laplace transform is s times q of s minus q of 0, which is our initial condition. Okay. Plus, we have a Laplace transform of just q. All right. So we have a 1 over RC that kind of sticks around, and we multiply this by q of s. Okay. And then on the right-hand side, we have 1 over r multiplied by the Laplace transform of our forcing function, which is E of s. Okay. All right, good. All right, so now that we have it in this form, our next step is simply just to solve algebraically for q of s. Okay. Okay. We'll go ahead and plug in our initial condition 2, right? So our initial condition q of 0, from the given problem, we know that q of 0 is some function that is our, or some value, that's our initial charge on the capacitor. Okay. So this is q naught. Okay. So we do that. I'm going to go ahead and move it to the other side of the equation because it's a known quantity. Right? And so on the right-hand side, we have S plus 1 over RC multiplied by Q of S is equal to, I'm going to go ahead and plug in for E of S as well, right? So E of S, you have 1 over R times E of S, which is E over S, E to the minus AS minus E over S, E to the minus BS. Okay. plus Q naught. Okay. All right, so now that we have it in this form, we can go ahead and solve for Q of S. And so all we have to do is just divide by S plus 1 over RC. Okay. And so we get Q of S is equal to, let's see what's the best way to do this. And so I'm going to factor out an E over S from both terms there. Okay. So we have E over R S times S plus 1 over RC multiplied by E to the minus AS minus E to the minus BS. Okay. So all I did for that first term was I just factored out like terms. So that both terms have an E over S. So I factored that out and I divided by S plus 1 over RC plus Q naught divided by S plus 1 over RC. Okay. Good. And then last step that we have here is we need to take its inverse. Okay. All right, so taking the inverse, and so we have essentially two terms here. So we have basically 1 over S times S plus 1 over RC. That one we're going to need to do partial fractions for. And then the other term is we have Q over S plus 1 over RC. That one we don't have to do partial fractions for. That one is ready to invert. Okay? Okay. So let's do this one first. Okay. Okay. So we have E over R times 1 over S times S plus 1 over RC. Okay. So we do the partial fractions. This is going to be 1A over S plus B over S plus 1 over RC. Okay. All right, so pretty straightforward. We just have a two-term or two expression partial fraction. Okay. So let's do the same thing we did in the last example. So let's multiply by the denominator. Okay. So the denominator being S times S plus 1 over RC. Okay. All right, so we do that. We get E over R is equal to A times S plus 1 over RC plus B times S. Okay. All right, just like the last example, let's go ahead and distribute and then group like terms. Okay, so we have E over R is equal to, we have two S terms, and so we have S times A plus B plus A over RC. Okay. All right, so we have two unknowns to solve for here. We have a pretty simple system, and so we have, if we look up at the constant terms, and so we have E over R on the left-hand side, this is equal to A over RC. Okay. The two resistances are going to cancel out, and so we get A is equal to E times C. And so then according to our first equation being A plus B is equal to 0, that means B must also equal what is equal to the minus of that, B is equal to minus E times C. Okay. Okay, so let's go ahead and plug those in, right? So now that we've done our partial fractions, so we have Q of T is equal to, okay, we have EC all over S, minus, excuse me, minus EC over S plus 1 over RC. Okay. And then we multiply this by our shifting terms. And so our shifting terms are E to the minus AS minus E to the minus BS. Okay. Okay. And then we can't forget our initial condition terms. We have plus Q naught over S plus 1 over RC. All right, so we're finally ready to take the inverse. Okay. Okay. So all of our functions of S here, except for the shifts, right? So remember, we're going to ignore the shifts first. We're going to take the inverse of the base functions first. Okay. Okay, so we have Q of T is equal to, we have E, the inverse of EC over S, that is just E times C, okay, minus EC over S plus 1 over RC. Inverse of that is EC times E to the minus T over RC. Okay. We're going to multiply that by our shifts. So we have E to the minus AS minus E to the minus BS. Okay. Plus our inverse of Q naught over S plus 1 over RC. That is a Q naught, E to the minus T over RC. Okay. But all I did in this step here is that, every expression that has S except for the shifts, I applied our inverse to it using our Laplace transform table. Okay. All right, and then last step, finally, we can go ahead and apply our shifts. Okay. Okay. Now you have to be careful here because we have technically a foiled expression here, right? So first term here. So let me actually do that first. Right, so we have Q of T is equal to EC minus EC E to the minus T over RC. Okay, we're going to shift this one by amount A. So this is multiplied by E to the minus AS minus EC minus EC times E to the minus T over RC. E to the minus BS. Okay, so there's basically, it's you want to be careful when you have these kind of FOIL terms here that you kind of distribute things appropriately. Okay. Plus Q naught E to the minus T over RC. Okay, all right, so last step here is that we can go ahead and apply our shifts. And so we finally have Q of T is equal to EC minus EC. So the only term with the T here is the exponential. So we have E to the minus T minus A divided by RC, okay, multiplied by U of T minus A, okay, minus, same thing, but with the shift of B, okay. So we have EC minus EC E to the minus T minus B over RC, multiplied by U of T minus B, okay. And then we have our initial condition, Q naught, E to the minus T over RC. Yeah, I know. So these expressions do get a little bit hairy just because of all the shifts, right? But if you actually plot this function out, it actually looks very fascinating. You can actually see the effect of the switch turning on and off. Okay. So this is just trivia, right? And so, you don't need a magical kind of graphing brain to do well on the exam. But if you actually graph this out, it actually looks like the following. Okay, so this problem was very interesting because our capacitor actually started with a charge, right? So we had an initial charge in the capacitor, but when the battery is disconnected, what happens is that our capacitor is going to actually be discharging because there's nothing charging it, right? And so if you actually plot it out, it actually looks like the following in the first phase, okay? Right, so just like our function said, we're going to start with a value of Q naught, okay? In our initial phase here, before t is equal to a, right, our capacitor is going to be discharging, and so it's going to be looking like a decaying exponential, okay? So this section of the graph here corresponds to just this section, okay? Right? Because we haven't connected the battery yet, and so, if you look at the other components, the u of t minus a, u of t minus b, so those contributions are not even active at this point. So that means, we are, we're only considering that part. Okay. And then when t is equal to a, this is when the battery gets connected. And so the nature of our function shifts. Okay. So right here, battery connected. And so when the battery is connected, what happens there is that our capacitor will actually start to charge up. Okay. And so then our function, kind of starts to look like this. Okay. Right. So this portion here, so let me go ahead and draw in t is equal to b. Okay.
It goes up to the same Q naught value.
Not necessarily. And so the Q naught was just whatever the initial charge is. And so, what value it comes up to depends on how strong the battery is, of course. But, it kind of looks the same just because, I only have a limited amount of space here. But we can also overshoot this, right? So let's say we have a very strong battery, we could overshoot this and even go further. All right, and then finally, the last portion, right? Right, so the last portion of this solution, this u of t minus b, this one is not even active until t is equal to b, right? So when t is equal to b, this portion becomes active, okay? Right, and then what happens here, at least physically, is that our battery is disconnected again. Okay? And so when you plot everything together, right, and you actually kind of punch it all in, it actually starts to look like this, right? And it does exactly what you expect. So once the battery is disconnected, then the capacitor will start to discharge. So we have kind of a section of our graph that kind of looks like our first section. Okay. All right. So this was, relatively speaking, a relatively simple example. We were able to finish it in like 25 minutes. But hopefully you can kind of see that, with our step function, we can kind of really model really interesting phenomena like this. Whereas if you try to solve a problem like this in the normal way, it would be very difficult to do. Okay. Basically, every time we change colors, there would be a separate problem. So this is, obviously much easier to do in Laplace. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. That's all we got time for. All questions.
It's going to go over Thursday's material to finish the homework.
Yes. So Thursday is all going to be on impulse function. So I don't think it'll take the whole time. Impulse functions are relatively simple compared to step functions. And so we'll probably do half impulse functions and then half the next thing. But impulse function will be the last thing on the midterm. So that's going to be the cutoff for the midterm.
Okay. So with this, we can do up to the last one.
Yes, you can do up until everything except for problem. Right. All right, so remember, I'm going to post the poll today about the midterm date, so make sure you answer that. Make sure you vote for that, so we know, so that everyone kind of knows what date the midterm's going to be. All right, so thank you guys for coming today, and I will see you guys on Thursday.
B is asking for an example of an impulse.
Yes, yeah, oh yeah, so that one we'll have to wait till third.
Okay, so is it gonna be a lengthy, is it?
No, it's both of them pretty simple. Once you get step functions, impulse are very good.
Good question. What we did when it was mismatching, I'm not really sure what happened here. Like,
Yeah,
what's the man?
so the kind of the logic behind this is that it's shift 10 right here, right? Okay, so the thing that you do is that you kind of pull the shift out if we have this e to the minus 10s. Okay, and then we kind of apply the reverse of that shift to our t. So in for t, we're gonna plug in t plus the opposite of that shift. Yeah, and then but then that minus 5 is still there, so that's why it's
Okay,
yeah, and then we just do t plus 10 minus 5, we do t plus 5.
and that's how we get it to match.
Exactly.
All right, cool.
Thank you so much.